let's go. Last time, what did we do last time? Right, we talked about Haar measure. Okay, so we had additive Haar measure. We did two integrals, one with additive Haar measure, that is, i.e. on QP, together with the additive structure, which we said should measure if I have some random point in QP, and I take ZP and I shift it either forwards or backwards by some power of P, then the measure of that should be just like the p-adic absolute value should be p to the minus n. And that'll make ZP have this compact set ZP have measure 1. We also looked at multiplicative Haar measure. Multiplicative Haar measure. So in the same way, I mean, this is really the integral over this a plus p to the minus n ZP dx of 1, right? That's what this measure is. So the multiplicative Haar measure was that you integrate some nice function f of x over, well, it only takes values in the multiplicative p-adics, and d star x, or d mu star, if you like, or just d star x is how I'll write it, is that you integrate, it's the same integral, but you integrate dx, that's the additive measure. So there's an additive measure dx, divided by the p-adic absolute value of x. And yes, there was a normalizing factor, p over p minus 1, so that the multiplicative measure of the group of units is 1. That's the new normalization. This normalization, I guess I didn't say, came from, I mean, we just started with calling ZP a set of measure 1. And realize that all the other measures, if it's going to be invariant under addition, have to have this size. If we want a measure that's invariant under multiplication by QP cross, then we need this.
Still feels a little weird. So it feels like it works for this, but it might not work for other things. I don't know.
Well, it's just a normalization, but we saw some integrals coming out rather nicely and rather what's it called? When you forecast what's coming, rather ominously. That's the word. Thank you. Rather ominously, we had a calculation. That's exactly the word I was looking for. All right, then we were talking about Fourier analysis. So we needed an additive character. So we were looking for some analog of e to the 2 pi x, and the analog of e to the 2 pi x was e to the 2 pi ix. So the additive character is the map that takes x in QP to e to the 2 pi ix, with the understanding that that infinite part is an integer. I mean, pretend it's an integer, it's sort of a limit of integers, and e to the 2 pi of an integer is 1.
Maybe
So
just define the map that way.
you could define the map that way, yes, but I find it sort of less insightful. Well, I mean,
carrying
it's
out limits is a...
That's right. We don't want that's an a0 plus a1 p plus a2 p squared, and so on. So there's this infinite limit that makes this not an integer, but this is all in ZP. And this gets mapped to e to the 2 pi I, just this first part. I don't know if you want to call it the principal part, p to the minus n plus a minus 1 p to the minus 1.
And when you map these, you're choosing like your representatives of numbers modulo p as like 0 to.
This is literally e to the 2 pi I, p to the minus n, and then yes, these things are all the AJs are in all of the AJs are in 0 to p minus 1.
Right, because otherwise you might guess.
Actually, no.
Right, because it like just carries over.
Because it just, well, okay. Yeah, this is a p to the minus n. So this, I do need this to range in 0 to p minus 1.
Yeah, otherwise
Yep.
it would be well defined.
Yes, but then it is indeed a character. That's what we checked. That if you have two of these, when the way that carrying would work,
It would work well.
it works the same way. Would be compatible with
The
this.
problem is if you let it range, then you might have the carry might not go the whole way, right? If you just like change one digit and not like.
Oh, I mean, I can't represent this as, I can't put a p here. Or p plus 1. right? Instead of a 1. If this first digit is supposed to be a 1, I can't put a p plus 1. That p plus 1 belongs in the previous power
What
of
if
p.
instead of 1, you put like, -1?
Right, so that -1 is really like there's a next p that -1 should be p minus 1 plus p. So it adds a power of p somewhere else. Okay, so I really do want these to be in 0 to p minus 1. Okay, and then did we define, how far did we get? Did we define a Fourier transform? Let's mimic. So we're going to mimic Fourier transform. Fourier transform. So we'll take a function. Now, what's a nice function? Right. With this, I remember we did discuss the analog of Schwartz class. So f analog of Schwartz.
Indicator function?
Well, we didn't call it an indicator function. We called it locally compact. Locally constant. Right. We want it to be locally constant and compactly supported. So that's the analog of Schwartz, please.
Regarding compact support, for QP, doesn't that mean that literally the values where the function is supported has to be compact, not its closure? Like over R,
that's right.
Support, we take the closure of the.
Yeah, you can take the or you could just say there is a compact set so that whatever the support is contained inside that compact set. You don't have to specify what that compact set is. You can take one that's a little bigger than necessary.
Problem is you can take absolute value on ZP take away 0, and then that function is locally constant and certainly has support inside a compact set, but it's itself not a finite sum of indicator functions.
You're right. So we discussed this. So let's just think about this for a second. Okay, so you're saying that the support that the closure support literally needs to be a compact set.
The support no closure literally needs to be compact.
Meaning that the closure compact. So the support itself,
Yes.
Is compact.
Without taking closures, correct.
Yeah, maybe you should spell it out kind of explicitly.
Yeah. I'm just thinking. Okay, so let's talk about this for a second.
I didn't realize it until like 2 days ago.
So we discussed that ZP take away 0 is indeed an infinite disjoint union of units shifted by p to the n, disjoint union over n. Right, this is like where except for 0, there's a first non-zero digit. So that's this p to the n, zp to the n. Now you're saying, let's say I have a function that's
the absolute value function on that domain.
The absolute value function on that domain is certainly locally constant because around every point there's an open set where it takes one value. The support is contained in the compact set ZP.
Right.
Okay, so let F is absolute value on this set ZP minus 0. Okay, so this is example. We're working through an example of what this thing means. Compact support. Do I literally mean the support is compact? Right. So the support is contained in ZP. The closure of this thing, limits of this, the only point that's missing from the limit is 0, since it is a limit of things with zeros as the initial digits. The closure of the support is ZP, which is compact, but F is not a finite union of indicator functions. But F is not a finite sum of indicator functions.
How is it that we could represent indicator functions?
Well, so what I was saying last time is if the support, okay, so then I really am talking about the support. If the support itself, so this compactly supported means the support of F is itself compact, not its closure, not is contained in the compact set.
Define this part to be the closure of that page.
That is how you usually define support, but here we're getting into a little bit of trouble because what I had said before. So let's look at this argument. Here's the support, right? The support. Let's say the support is just contained inside some compact set. So this is the support. This is a compact set K. This is my compact set K. Okay. Around every point of F. No, so something's wrong. Let me make this picture bigger. This picture is too small.
And this is like compact in the, p-adic topology.
Yeah, in the topology that we put on the, which is generated by open sets of the form that we discussed. Okay, so here's the picture I have in mind. Here's a compact set K. Okay, here's the support of F. So around every point of F is locally constant. So around every point, I have open ball. Those open balls are not necessarily a cover of K. What I said last time is, so you take these open balls, yeah, there has to be a finite subcover, but they don't necessarily cover K. They do cover the support. So the fact that the support is contained in a compact set, or that the closure of the support is a compact set, does not mean that these open balls cover all of K. And indeed, that's exactly what's happening here. These open balls, the open balls on which F is constant, do not cover a compact set.
Isn't the absolute value constant at zero?
It is locally, oh, no, it's not locally constant zero. Every neighborhood is zero case.
But for any point in here, when I take away zero, for any point in this set, around it is a neighborhood of, I can put a ball by specifying the first two digits, making the rest of them free. So that's so this is locally constant. So this on this thing is locally constant. Very good, very good. It's good to get this stuff straight. Is locally constant. Its support is contained in a compact set. The closure of the support is a compact set, but F is not a finite sum of indicator. So that's great. That's great. Okay. So I do want, not compactly supported means not the closure of the support, literally the support is itself compact. Okay, because what I want to have happen, I mean, I'm sort of cheating. I'm messing around with the definition until I get the behavior that I want. Isn't that what we always do anyway? So the consequence. So then, so now the compact set is the support. And so if we have an open cover, then there's a finite subcover, then F is a finite sum from 1 to n of indicator functions of balls, p to the nj zp.
And then
Okay.
these compact sets should be like finite unions of like things like ZP.
Well, exactly. I mean, the support, here's the support. Here it is. It's the union of these finite guys. All right, that makes it very easy to do certain calculations. So we're going to define by analogy. So by analogy analogs, we're going to define the Fourier transform of locally constant. So again, F is okay. It's clear that I want F to be locally constant, and the support being compactly supported. I'll define the Fourier transform to be, you take your function, you multiply it by your character, e to the 2 pi I x times c, and you integrate with the additive par measure over all of QP. All right, let's see if we have a Fourier inversion theory. What's a Fourier transform? What's an inversion?
And C is in QP.
C is in QP, exactly right. So it takes functions on QP to other functions on QP.
Inverted.
That's exactly right. That's exactly right. So we're taking, that's the other. So the function, I mean, the function is from QP to C. So the function takes values in C. So this takes values in C, and this is a function that takes values in C. But the arguments are QP. That's right. Okay, so here's the exercise. Did anyone do the exercise? Did I make it an exercise, or I just say next time we'll do it? I think this is where we left off. So far, everything has been reviewed. What is the Fourier transform? So let's just forget about the constants. Obviously, the integral is linear. This is a finite sum. So I just need to compute the Fourier transform of one of these sets. Now I know everything about Fourier transforms on p-adic numbers. So the calculation that we need to do is to take the Fourier transform of the indicator function of some a plus p to the n zp adic c. Does that make sense? This is the indicator function of one of these balls. What is its Fourier transform? If we know that, then we know everything about Fourier transforms on locally constant compactly supported functions. You want a minute to do it? Or should we do it together? Who wants a minute? Nobody. All right, let's do it together. All right, let's do it together. So it's an integral over QP. The function is the indicator function of a plus p to the n zp, and then e to the 2 pi I. This is x is ranging over QP, x times this fixed number c dx. All right. The beautiful thing about indicator functions is now I can restrict x to be in this set, a plus p to the n zp. And then that is the indicator function. So that has restricted the range. And now I'm integrating e to the 2 pi I x c dx. So far, so good. All right. Let's make a change of variables. X goes to x minus a. So if I integrate instead of, or rather x goes to x plus a, if I integrate x plus a times c, then the range, the first thing like this, that should be the set of all a plus p to the n zp's. So this is already a plus, and x should range in p to the n zp's dx. This is where I'm using har. Yes, in the invariance of the measure under this change of variables. So this is har. Now I'm going to use character. Now I'm going to use the fact that we have a character. Character is that there's this constant e to the 2 pi I a c that's going to come outside. E to the 2 pi I a times c times the integral over x in p to the n zp e to the 2 pi I x dot c dx. So far, so good. These are completely standard manipulations. All right, this is a complete integral, right? X looks like a n p to the n. I don't know if n is positive or negative. Plus a n plus 1 p to the n plus 1, and so on forever. The a's are totally free. They range over the entire set of residues mod p, from 0 to p minus 1. Let's say if the absolute value of x dot c, the p-adic absolute value, of course, is less than or equal to 1 for all x in this range, for all x, then what happens to the character? This product has absolute value less than 1. In other words, it's in ZP. If this is in ZP, i.e., too much then, i.e., x dot c is in ZP for all x. Yes, exactly. Then e to the 2 pi I x dot c is identically 1. And then the integral, in which case this integral, e to the yada yada, which is the integral of 1, is the measure of this set. What's the measure of this set? 1 over p to the minus n. Okay. Now, what does it mean that x times c is less than 1 for all x? Well, this, by definition of norm, this is the absolute value of x times the absolute value of c. Now, what is the absolute value of x as x ranges over p to the n zp plus? The absolute value of x, I mean, what's a lower bound? It can get, yes, exactly. This is at least 1 over p. 1 over p to the n, p to the minus n. Yeah, what am I trying to say?
Go to 0. X can go to 0, so it has to be small.
Yeah. So in other words, the x is bounded by p to the n, and the norm of x times c needs to be bounded by 1 for this behavior. That means the norm of C. So this happens if and only if, in fact, CP is less than P to the N. Yes, let's go over that one more time. What does it mean that for every X in P to the N ZP, X times C has norm less than 1? I claim that happens when C itself has norm less than P to the N, because X, if C has norm at most P to the N, and X is going to have norm at most P to the minus N, then their product is going to have norm at most 1. Does that make sense? And of course, that's the case if and only if C is in P to the minus N ZP. Okay, so that's case 1. This is case 1. Case 1, it turns out, is the case that C is in P to the minus N ZP. Then we get this calculation P to the minus N for the integral. And there's this constant out front.
C is the argument of the Fourier.
C is the argument of the transform, exactly. C is what we're putting into the transform function.
Let me see what happens when.
That's right, case 2. Case 2 is that C is not in P to the minus N ZP. Please.
So I problem using this equivalent X is like most people.
Yeah, so it's for all, the point is this is something that's just, this inequality holds for all X. If and only if CP is at most P to the N.
So you can play around with it, towards
That's right.
this.
Yeah, now I do.
Yeah. It's the for all X that has to be added there in order to make this inequality. That's why in my mind, I was like, don't I want this a less than sign because I want to divide by that? No. It's the for all X.
Yeah.
That means that upper bound here induces an upper bound is if and only if we have this upper bound.
All X in CP?
All X in the range for all X that range. Yes. So for all X, let's be precise, in P to the N ZP.
P to the minus N, P to the 2 pi I base side.
Yes. So I said just the integral part
Oh,
is P to the minus N, and then there's this constant in front. Yep. Case 2 is that this is not in P to the minus N ZP. Well, that means it has digits farther to the left of whatever P to the minus N is. Then, well, let's say there exists X in P to the N ZP such that the norm of X times CP is greater than 1. C is fixed. X is ranging over all possible values.
I mean, now these are actual individual elements.
Now now we have a real character. We have a non-trivial character. So that means that e to the 2 pi I xc varies with x. Otherwise, it didn't vary at all, right? In case 1, this is just identically 1 for all values of x in this range. If it does vary, it varies over a complete set of residues. And does so over complete set of residues mod p for every single coefficient that's sticking out of this product with C fixed.
Right, so you're gonna have like some non-trivial fraction, right?
Yeah, I'm gonna have a non-trivial fraction. I'm gonna add all of them around the circle.
That's what this is saying.
Yeah. So what do I get? 0. So exactly. So the integral comes out to 0. So wait a second, check this out. Check out what this means. Okay, does everybody follow this argument? It means that when you take this product, there are some terms with negative p's, negative powers of p. So e to the 2 pi I of this product actually has some character. Whatever that character is, it's going to be summed over x runs over all the residues. I mean, the elements, the digits, the p-adic digits of x are freely running through all the elements in Z mod p.
Well, when most times all have the same number, that's still.
That's right. That's right. Because there's some non-zero digit here, for the xc. That's what this means. There's some non-zero digit for the xc that's multiplying the x's, and we're summing over all of them. So they're going to cancel off. So what does this mean? This integral, so this exactly is the Fourier, whoops, I want to not leave you out, good friend, range of x. So this integral comes out to either 0 if c is not in p to the minus n zp, or it comes out to, so now I have to put everything together, e to the 2 pi I a times xc times p to the minus n. Else. Let me record that in a better way.
So the simple
Select.
function is with this distributed, right, the linearity.
That's right. But it's even better than that. The Fourier transform of a simple function is itself a simple function, but not the same one. So what we've proved, let's call this I don't know if it's a theorem or a lemma or something. The Fourier transform of the indicator function of one of these sets is, what was it? I'm going to keep this here for a second, then I'll delete it. I just want to keep it so I can write it down. It's e to the 2 pi I a dot c, complex number, times p to the minus n, complex number, real number, times the indicator function of the set p to the minus n zp. And that indicator function is testing whether c lies in this set or not. Now I don't need this, this stuff.
Why isn't it complement? Why isn't it complement?
It's 0 if c is not in p to the minus n zp,
Oh, not.
and 1 otherwise. That's not a simple function. It's an indicator function times a constant.
Nothing very C.
You're right. This is not a simple function, but it's a character. It's a complex number. I mean, it's a character times a simple function. Yep. Thanks. So look at what happens. You have translation here. This is exactly what happens for Fourier transforms, right? Sorry?
It's simple when A is.
It's simple when A is 0. Yes, okay,
Which is the
fine.
most popular one.
Heck, I've never even seen this. I've only done it for 0.
No, you have to do it for general A. What do you mean you've never seen this? No, this is crucial. How are you going to invert the Fourier transform if you? But that's not the generic. Anyway, whatever. But this is something that happens in standard Fourier analysis. When you have translation and then you take a Fourier transform, you get translation turns into rotation. And then a scaling of p to the n turns into, on the transform side, some constant 1 over that scaling, and scaled 1 over the other side. You guys know what I'm talking about? That's exactly where we're going. Yes. We're headed towards Adelic Poisson summation. That's our big goal. But we have to get to the Edels first, and we have to get to Fourier transforms first, and it recurse backwards. So it's not going to be that long. I think we have a good chance of getting a good chunk of it done today, in fact, if we can. But does this make sense? Is everybody following what this calculation did? So the Fourier transform of the indicator function of an open ball is some phase shift times the measure of the ball times the indicator function of the sort of correspondingly opposite ball. If you had lots of digits to the front, now you need only digits to the back, and conversely. Okay, so how do we invert a Fourier transform? So I claim, so let's calculate if I take a Fourier transform of a function, how would I usually invert it? Exactly. I take the opposite or the conjugate character, I integrate over xc, taking values in QP, and with respect to additive power measure on C. Let's see what this is. Maybe we'll get lucky, it'll come out to f of x. Okay, so what is this? Well, this thing, so when we'll calculate it in the special case, which is not so special, it's the generic case, when f is the indicator function of one of these a plus b to the n ZPs. Okay, so I know what its Fourier transform is. I just wrote it down right there. So this is an integral over C and QP. This function is e to the 2 pi I a times C, p to the minus n. And then the indicator function of C being in p to the minus n zp times e to the minus 2 pi I x times C dc. Is everybody happy with that? I just wrote in what the what our calculation told us that the Fourier transform came out to.
Much nicer than having to do it inside.
That's right. That's right. Once you've computed it, I'm telling you, we should learn p-adic Fourier analysis before we learn real. It's just, it's trivial, so easy.
Maybe finite Fourier analysis.
That too, yeah, yeah. Characters. Okay. This is a character. This is an indicator function. Okay, so I'm integrating over C just in p to the minus n zp. I have a character e to the 2 pi I a minus x c. And there's this factor of p to the minus n in front. dc. Yeah? Does that make sense? If only we knew how to integrate stuff like this. It's exactly the same formula, right? The indicator function of a character, now it's integrating C instead of an X, but it just depends on whether this A minus X, so we get either, depending on whether A minus X is in P to the N ZP, if A minus X is in P to the N ZP, then when I multiply it by C's in P to the minus N ZP, I just get 1. And the integral is just the measure of p to the minus n zp, which is p to the n. Now, should I extend this a little bit so that we get a complete, yeah, we can keep this constant p to the minus n. So we just get 1. Now I'm taking the whole thing. So as p to the n, the integral comes out to p to the n, there's a p to the minus n, just comes out to 1. And else, if this is not in p to the n, then I get a complete set of residues for some digits of C, and I get 0. Also known as the indicator function, right? There's a function in X. When is A minus X in P to the N ZP? Well, -1 is in ZP cross. -1 is a unit. So A minus X being in here is the same thing as X minus A being in here, which is the same thing as X being in A plus P to the N ZP, which was the function that we started with. So that's Fourier transform and Fourier inversion in the p-adic numbers. Okay. Trivial. Amazing. All right. Good. Okay, let's get to Adeles. So have I done everything I wanted to locally? If not, I'll come back to it. And I think I've done everything I wanted to locally.
So only how really
On the p-adic components, but now we want to put everything together. So let's talk about the Adeles. Adeles, the A is these are the additive. I mean, these days the Adeles are kind of more important than the Edels, but the name is that they're the additive Edels. And the Edels came from Chevalet's theory of ideal elements, which goes back, I mean, anyway, there's a long history here. We'll get to what the Edels are. Maybe you don't care. The Adeles, we have all these embeddings of Q into the real numbers and all the QPs. The naive thing to do is, well, let's just multiply them all together. R cross the product over all primes of QPs. Let's take all of so these are just infinite sequences. We'll take the direct product of these nice locally compact spaces. And let's see if we can make sense of this. So the first hint that this is trouble. So let me put a question mark here. Right, this is a Cartesian product. The first hint that there's trouble is we can define an Adelic norm. The Adelic norm of X. So now X is an element of the Adeles. What's an element of the Adeles? It's something called X infinity, which is a real number. So actually type theory is quite useful for this. This is of type R. Then there's X2, which is of type Q2. Then there's X3, which is of type Q3. Then there's an X4. Okay, good. You're paying attention. There's an X5 of type Q5, and so on, right? So it's just this infinite sequence, X infinity, X2, X3, X5, X7, X11, and so on, indexed by the primes, and it's one for each component. It's exactly what a Cartesian product is. Right? And each of those components is itself infinite equivalence class of Cauchy sequences. Yes, it's a rather.
Okay, so that's true. Have like a tuple of things from R.
That's true. That's exactly right. Think about how you're going to implement this in Lean. People have done it. So go see how they've done it. All right. So what is, well, let's try to put an absolute value on the Edels. It's the natural one. Yeah, let's just take the product, right? X infinity infinity times a product over all primes of XP P. Sorry. Well, if you really want the product structure, then this is the natural thing. And by the way, we computed, if you guys recall, let's just call this recall, P.
When we do products, and we are split, you don't take the product.
That's true, but this is somehow much more, that's because they sort of talk to each other better than these. These are kind of independent, but let's recall that if we have any rational number, I'm so used to writing QP now, Q.
So even if you use the super norm, like it'll still.
You guys will see in a second. What happens if we take the product over all primes? I'm going to get tired of this. There's nothing special about the infinite one. There is. It's the only Archimedean one. But I'm going to write P less than or equal to infinity. Okay, where P equals infinity is this guy. So what is the set? So okay, I should have said this. How do the rational numbers sit inside the Edels? They don't really sit inside the Edels. There's actually a coercion into the Edels for the Lean people. How do I take a rational number and map it? So I have a rational number. I'm going to map it into an Edel.
I would just.
Diagonal. Yeah, go ahead. Diagonal.
That's correct.
Oh, what were you going to say?
I was just gonna say, send it into R and then say everything else.
If
I don't think it wouldn't work with the rest of it wouldn't work with the metric on the Edels. You wouldn't still have the same metric.
Right. So what I want to do, well, I have an embedding of Q into R, and I have an embedding of Q into all the QPs. So just do them all. So that's called the diagonal embedding. I put Q. Now I could just write Q, but these Qs, they're all completely different numbers. This is a Q. This is where their type theory is useful. Yes, this is a Q of type R.
Put up arrows on all of them.
Yes, up arrows. Yeah, where each up arrow means a different coercion, right? So this is a Q of type R. This is a Q of type Q2. This is a Q of type Q3, Q5, and so on. So they're all completely different infinite sequences, but they come from the same number, and that's our embedding. And so if I take the product over all places of that local valuation, of that local absolute value, we computed this. It's one. Exactly because the denominators and numerators give us positive and negative powers of whatever the prime factorization is, and the real place is just the rational number itself, which gives back exactly this.
We chose normalizations which work, right?
We chose exactly. This is one of the reasons that we like that normalization of the p-adic norm being not just some arbitrary number less than 1 raised to the valuation, but 1 over p raised to the valuation. Exactly. Very good. I left room here for that. Okay. That's actually going to be very important in just a second. Okay. So we have this embedding of the rational numbers into this version of the Edels. This is a nice norm. All the rational numbers have absolute value 1. Rationals are nice. How about this element? So I'll take 1 in the reals. I'll take a half in Q2. I'll take a third in Q3 and a fifth in Q5 and so on. And what is its norm? Yeah, 2 times 3 times 5 times 7. Yeah. So what's that? So this is bad. This has Adelic norm. If it's meant to be an Adelic number, it has infinite Adelic norm. That's not so nice. I mean, the Adelic norm is the norm anyway, because there will be lots of numbers. By the way, we should see that already. Lots of numbers will have, like, if I just take something, if I just take a number, take random x in, let's say, -1, 1 cross all the ZPs, the product over P's of ZPs. This should be a very nice set, right? This is like, well, this isn't compact, it's not closed, but fine, I'll make it compact. Okay, so if I take some compact thing in R, cross all these nice compacts in all the ZPs, that product had better be a nice product. So if I take a random element here, what is its Adelic norm? Typically. Well, all the p-adic norms are going to be less than 1. The R norm is going to be less than 1. Your distance to 0 is at most 1. So I'm multiplying all these numbers less than 1. Yeah, a random element will have norm 0. So that's not an absolute value, because the only thing that's allowed to have absolute value 0 is 0 itself. Okay, so sorry, say it again.
You also just do 0 and 1 coordinate and bounce 0.
That's right. That's right. But it's much worse than that.
Yeah.
Like a typical element has norm 0 in this nice compact set. Okay, so there's a bunch of other things that go wrong. Sorry.
I said, so just quotient out by the things of norm 0. Big deal.
You do not. Well, then you're quotienting out by that entire compact set. You don't want to do that. Okay, so what's the right thing to do is not to take a Cartesian. There's something much worse. I mean, this is just messing around with the norm. When you take this product, you get something that is no longer locally compact. And to have any hope of a Haar measure, the existence of Haar measure uses the space being locally compact. Yes, a Haar measure on the big thing. You want a Haar measure on the Adeles. We're going to want to do Fourier analysis on the Adeles. All of this was building up to Fourier analysis.
Why did people start doing things like this?
It's a very natural thing to do once you've done it. Yes. So, okay. How do I say something without going to class field theory? The Edels are very natural. Like the understanding of Edels is very closely connected to class field theory, which is what people, in the early 1900s, early to mid 1900s, were proving like everyone and their brother was working on class field theory in number theory. And the additive Edels ended up having even more, like once you're using the Edels, should I tell you what the Edels are? Well, I haven't finished telling you what the Edels are. The Edels are going to be the same kind of idea, but we want the multiplicative structures everywhere. And then we'll have similar problems.
You can say it after.
Yeah, I'll come back to what, yeah. So in hindsight, this is very natural.
Sorry, why not stick to sequences with one?
That's exactly what so the Edels will be sequences that eventually have norm 1 because of what we're about to do to restrict this product. That will be the case for Edels. And that's one of the reasons they're so useful. And to prove like class number formula and reinterpret all kinds of class number formula over arbitrary fields, not just number fields. There's a whole big industry here that I'm completely suppressing.
Norm 1, well, norm 1 in 0 is weak. You lose that additive structure.
Well, that's why the Edels have a multiplicative structure, exactly.
If you add 2 Adels to norm 1, they probably don't have norm 1.
Yeah.
And that's bad.
Okay, so we also, let me just remark, not reals, remark, Cartesian product. I said this, but I just want to write it down. Cartesian product is not locally compact, no nice Haar measure, Fourier theory, and so on. Haar measure, Fourier theory. dot, dot, dot. Okay, so what we're going to do instead, I mean, again, this was done first for the Edels and then the Adeles, but instead, what we're going to make the Adeles be is the reals cross a product over all primes. Well, I guess I've already put the infinity prime out here. QP looks exactly the same. I'm going to put one little thing there. That's the difference. Okay, so what that means, this instead of a Cartesian product is a restricted product. So what does that mean? i.e., this A is the set of all x that look like x infinity in R, x2 in Q2, x3 in Q3, and so on, such that so each xp for all p less than or equal to infinity, each xp is in QP, but almost all of them, all but finitely many, so this is the restriction, all but finitely many xp are actually in ZP. At most one, have norm at most one. So norms can't blow up anymore. They can go to zero, many do, but they can't blow up anymore.
So we did this so we can have a meaningful notion of engagement here.
We'll get all kinds of great benefits from restricting the product. This is a locally compact space. We're going to have a Haar measure. We're going to be able to do Fourier analysis. We're going to be able to do
So
great things. Yes, it also arises a natural inverse limit.
this is natural in the sense.
This is very natural, yes. And by the way, remember our embedding, so that with this new definition, is Q even in this? We changed the definition. Can we embed Q diagonally anymore? Why? We better be able to if we're going to do something. Does Q still embed in here? Does Q still embed here? The answer is yes. And why? Sorry, Joe, you're saying?
Are the denominator.
That's right. Yes. And that's literally what we're, finitely many things. Finitely many. Yeah, the numerator doesn't hurt us. The denominator, 1 over P, has norm P,
I see.
has absolute value P.
And then it's only like finitely many times the numerator or the denominator. Anyway, so
Yes. So all but finitely many of these are actually in ZP cross. Anyway. Yes, finitely many things are in the denominator. Okay, so Q does still embed in here. And this, I'll leave this in the interest of time. I'll leave this as an exercise. This is indeed a locally compact space. This restricted product, this A, is locally compact.
the topology we're getting.
Yes, let's give it the what's the topology? Under the topology,
What is this?
what should an open set be? Basis of open sets. So I'll have a U, well, let's do it like this, a product over primes in places, in some set of places S. Let me see this. Primes in S. So I have a finite set S of places of some open sets UP cross all of the other ones, all the infinitely many. I'll just put ZP.
By the places you mean like individual.
Yeah, place means a prime or infinity. And if you have a general number field, then you have other embeddings of the reals into of your thing into. I'm going to generate the topology from sets of this form.
Only by taking units and then taking exceptions to it.
Finite intersections, arbitrary unions.
And when T equals infinity, ZP means the interval minus 1.
For example, although you could always ask infinity to be contained in S, in which case this means a regular open set in the reals.
You're gonna use this sort of things to describe the rings of integers.
We're definitely going to talk about the ring structure of the Edels in just a second. Yeah, in fact, let's do that right now. Can I add to Adeles? Can I add Adeles?
So UP is part of real, right?
Yes, part of one of these is real, if you like. Yeah, take a real open set, cross a bunch of open sets in QP, but I'm controlling how many of them can be outside of ZP. All but finitely many are in ZP, are in fact ZP itself. You can take that as a basis. Okay, can I add Adeles? So this is, it seems preposterous. How could you not be able to add Adeles? But of course, if I have an Adel X and another Adel Y, their sum, if it's going to be anything, it's going to be the pointwise sum. But is this thing, when I take this pointwise sum, do I have any guarantee that knowing that X is eventually in ZP and Y is eventually in ZP, that their sum is in ZP? Why?
Like even if it were really disjoint places, right? It's still finite places.
Why? ZP is a ring. So this will have eventually, this is because of the ultrametric, right? The super triangle inequality. Eventually, XP plus YP is in ZP, which is a ring. Which is a ring. You take two things of absolute value less than or equal to 1, you add them, you cannot get out of 1. You cannot get out of ZP.
So does not apply in places like the reals.
That's right. But there's only finitely many places like the reals, in fact, 1 in this case. But right, I can add Adeles. Can I multiply Adeles? Can I multiply? ZP is still a ring. That's right. So I can still multiply for the same reason, right? Pointwise multiplication, right? Same reason. I can divide for the same reason. X divided by Y makes perfect sense. I just divide pointwise.
I mean, restricted to you're out.
Okay, yeah. Well, if Y is not equal to 0. Oh, okay. Maybe none of the components are 0. Now I can do it.
What?
I still can't. Even if it's non-zero, the norms might be less than 1, but they might be less than 1 for infinitely many x's. So when I try to invert, I get things with large norms for infinitely many p's. Okay, so no, I can't make sense of division at all. Okay, there's no, it's not a division ring. Yeah. Okay, so it is a ring, but it's not a field, not even close.
I thought you said it was perfect for everything.
You'll see, actually, we do not want it to have more structure than this. Yes. So now I can use the language of the ring. From now on, they've been upgraded, if they've been sired, the ring of Adeles, and not just the Adeles, you know. Okay. Does that make sense? All right. What else do I want to say about this? Let's I'm going to talk about the action. Yep.
Did you say this was locally compact?
It is locally compact, yes, with this topology. So I have to give you the topology. Here's the topology. I'll let you check that it's locally compact, but it's not hard from the fact that you know,
Does this give you weight?
component wise isn't enough because the direct product is also component wise
Is
locally
this the
compact.
same topology that the norm is gonna be?
Yeah,
On each component? you mean?
if I'm bounded, I don't think so. Because if I specify the Adelic norm to be bounded by something, I'm not specifying, I could have things that are, that,
But you restrict the norm to this space where things are eventually norm less than or equal to 1, then
yeah, it's a good question. What I'm concerned about is, you know, a basis means I can take arbitrary unions of things like this. Sure, I can, yeah, sure. But then I'm still, but now I'm taking, so an open set, I mean, this for on the basis, yes, but an open set will be an arbitrary union of these things. So we have to be a little more careful. I'm not sure. Let me think about that. So we have these Edels. We have this. Sorry,
What's the intersection of two of these based on?
it's just the pointwise intersection. But the point is the S's. You have to take the union of the S's. The intersection is that.
We have to take like finite intersections and then count away.
That's right. Arbitrary unions.
I mean, yeah.
So we have this ring of Edels. We have the rational numbers inside of here. And these rational numbers actually act on the Edels. How? Well, in the obvious way, translation, right? But let's recall. Here's a useful analogy. I have the integers. They sit inside the reals. Actually, they act on the reals, right? The real numbers, here's the real numbers. The integer, the group of integers acts by translation by some number of whole numbers forward and backward, right? If I have some set in here, if I have a set U, I can take the set U plus Z. And that's a nice translation, right? I can act by translation. In the same way, Q acts on the Edels by translation. So if I have a set in the Edels, I move, or just pointwise, if I have a point in the Edels, I move it by, so Q.
It's not trivial, move it by whatever power the time.
Just because addition it's a ring, Edels are a ring, I have this embedding of Q's. Yeah, given, yeah. And an Edel, all I'm doing is saying that's an action, right? This is a subgroup, a sub-ring of this ring. In fact, it's a group that defines it now in action.
Any more examples where we can see like behavior of elements of?
That's what we're building up to. Yeah, I want to understand what this behavior looks like. What's really going on here? Okay, so in exactly the same way, so Z, this action of Z on R, let's write this down. Action of Z on R is it a continuous action or discrete? Are the integers discrete in the reals? Yes. Okay, so the integers are discrete in the reals. This action is discrete. It's this continuous. Let me. Which notion do I want to use right now? Let's say discrete, i.e., around every point of Z. So let's say Z in Z, around every point Z in Z, there exists an open U that contains Z and doesn't contain any other element of Z, and no other points of Z, right? What can I take? So because Z is a group, I may as well do this at the origin. Nothing's stopping me from doing this at the origin, i.e. or e.g., for example, I take Z equal to 0. What can I take to be an open set around 0 that doesn't contain any other integer points? Negative 1 to 1. Yeah, minus a half to half. Negative 1 to 1 is the biggest set that I can take around Z that it's not going to have any more lattice points in. Yeah, minus a half. A half is a nice fundamental domain for that action. We'll get to that in a second. Well, here's the thing. Q can't possibly be discrete, right? It's this dense thing filling up all the real numbers. It's dense, right? Q is dense.
Well, that's in like the real specifically.
It's dense in the reals. What about Q? What about Q inside the Edels? Is it dense? Is it dense? Or discrete? Discrete? Something in between? No. So can I find an open set?
This is weird, like open ball structure.
Right. This is what I want to get. This is what I want to get our intuition wrapped around. What does this actually look? How does this look? Can I find, maybe not, an open set around, let's say 0 in Q, an open set U in the Edels, so U, A, can I find an open set around zero in the Edels with no other rational points? And containing, yes, containing no other rationals. Nobody else is allowed to be in there. You're saying it's impossible because I have the reals inside the Edels. That would be my intuition. The first thing I would think of. Right.
Even if that work contains a rational to even a product.
That's right.
Even if the first one-
That's right.
You need all of them.
I need all the components to be rational, but I need one set. I need one open set U that's going to contain zero and no other rationals. Other than Nick, I know you're dying to say the answer.
I don't know, I'm just watching.
Okay. But you know the answer.
I do. I
Yeah.
think about it.
This is really fun. If you can come up with this, then you're starting to understand. If you haven't seen this before, some of you have. If you can come up with an open set that contains no other rationals, but does contain zero.
So, close to zero. All of the things that you'll get have primes in the denominator that they don't have in the numerator. So if you take like P from each QP or
Yes.
each VP, or wait, that doesn't quite, that's like, no, just let each one of them be ZP. Any rational that's close enough to zero has to have one of them it fails to be.
So that is very, very close. We almost had a set here. Check this out. What about you? What about you? Let's take -1 to 1 in the reals, cross the product over all ZPs. Exactly as Joy is starting to get to, right? What about this set? The norm, the Adelic norm, the product of all the norms, restricted to you. All of these have absolute value at most 1, multiplying things at most 1. This has absolute value strictly less than 1. These are all numbers with absolute value strictly less than 1. Why can't it contain any rationals? Yes.
Is it because there's no primes?
It's because we know what the norms of any non-zero rationals are. The Adelic norm, this is the Adelic norm. The Adelic norm of any non-zero rational is 1. But on this set, all the norms are strictly less than 1.
So we're still using like the open ball of radius 1 to find the.
Yes, we're using the Adelic norm in this way, but that's not necessarily. I have to think about whether it's can be used as a basis for this.
Sorry, I got a little lost. What
Yeah.
exactly are we from zero, like U equal to?
Yeah. So here's this set U, which is -1, 1 in the reals, and then ZP on all the p-adics. I claim that if you take the Adelic norm, the product over all places of the norms, restricted to U, that norm takes value strictly less than 1, because it takes value less than or equal to 1 on all the ZPs, and it takes value strictly less than 1, whatever that is. It has no points with absolute value equal to 1. But for any rational number, we know that it's any rational number except 0. We know that its Adelic absolute value is exactly equal to 1. So this contains no, this is disjoint. So U contains no other rationals.
Open this.
And it's open. And it's of course open. It's one of the basis elements. I've got an open in R and opens and ZPs at all the primes.
I'm sorry. Often, like when products like that are built, the topology is not products of ZP, but products of PP eventually, right?
That's right.
Typical set. So this is a non-standard.
Well,
topology. It's a different,
No. So we want to take, we can take open sets in QP, but only for finitely many QP. The rest all have to be ZP. That's this restricted topology, the restricted product topology. And so the set that I'm taking,
like that, then there is no, the topology is the same.
well, no. So all I'm saying is that this is a set that's open in that topology. I just take the set S to be infinity only. Well, these are all individual cylinder sets. The ZPs are all cylinder sets, and I'm producting all of them. So they're all compact. So I have this product of compact sets, and I have this. I mean, they're compact opens.
You understand what I'm saying, right? Like,
I don't.
I'm saying that, like, I would expect it to be product of PPs, or cylinder set to be products of PPs, not of CPs.
But the QPs are too big.
So yes, we're using a different topology from what one might normally put on a product.
Right. What you're saying is correct.
Yeah. So it's the question about the Cartesian product topology
Right.
as opposed to the restricted topology. Yes, we definitely want the restricted topology. We do not want products of QPs. Here, we want products of ZPs. We want this compact. That's right. Product of QPs is not a subset of the Adeles. Arbitrary products of QPs are not restricted. And when you restrict it, it's the same thing as this. And this is exactly what we're doing. We're taking some number of QPs are allowed. QP is open in itself, so some number of QPs are allowed here, but then all but finally many have to be ZP. So the upshot of this is that the rational numbers are discrete. They're not dense, they're discrete in the Adeles.
Sounds good.
So Q acting on A, you might start thinking of as Z acting on R. That's kind of one kind of picture you can try to, yeah. Now
If you translate that neighborhood around zero, get a neighborhood around X.
that's right. Exactly. Because it's a group action. Yep. So all we needed to do is take it at a single ration.
This is sort of like saying you were targeting really close to something, then you had to be p-adic because you're rational.
That's what this thing is. Exactly.
How do we know multiplication and adding is continuous?
That multiplication addition is continuous in this topology. Yeah, you have to check that.
Okay.
Yeah, it's not hard.
Yeah.
If they differ at all, then they differ. Yeah,
You can't like bring close to zero in the R one without taking like really big fraction.
that's exactly what this. Yep.
It's very crude. But it works.
Yeah, that's exactly right. You can't get close to zero in Q with the Adelic absolute value. All right, let's what can I do in the remaining time? What I want to get to is a fundamental domain for this action. So for Z acting on R, we know what a fundamental domain domain for this action. Yeah, it's a fundamental domain. So I want a domain D. D is a subset of R. So I just want to know what R mod Z is. R mod Z is a circle, right? Or it's a unit interval, 0, 1, where I've identified the two endpoints, right? These are all fundamental. So I would like to have a notion for them. So a fundamental domain for this action, it depends on how you want to do an open domain or an exact domain. Like you could say the open set 0, 1, any point in R can be moved into the closure of 0, 1 by an element of Z. and any two elements in 0, 1 that differ by an element of Z are the same element. And the difference is 0. That's the kind of idea. You could also use closed. What do I want to do? Let's do open. Yeah, let's do open. So a fundamental domain for this action D is an open set, or in general, a fundamental domain for i.e. D is an open set. D is open. For all R in R, there exists a Z in Z, such that the action, which here is addition, can get you to D. Well, it's open, so I might have to get to the boundary of D. And if R and R prime are in D, and R is equal to R prime plus Z for some Z in Z, then R equals R prime and Z equals 0. Exactly once, yeah. So I want it to be uniquely, every element in the quotient has a unique representative in D, and everyone has a representative in D, and that representative is unique. That's all. So these are the two conditions.
You don't need uniqueness on the back.
We also need a.
That's right.
Discrete condition on.
So if I have a discrete, yeah, so this is a general definition for a discrete action. If I have a discrete action of a group on some arbitrary space, a fundamental domain for that action is an open set in the topology of that space, so that every element of the space can be moved into that domain, or at least the closure of that domain, by an element of the discrete group, and it's unique, and that action is
Like generally, you can't replace Z with any, right? It has to be, or you can't replace Z with anything, right? There
So-
actually has to be discrete.
So if I have a group G acting, that's right. For there to exist an open domain, this action has to be discrete. So it's better to write gamma in that case. So if I have a group gamma, and I have an action, so if I have a group action, discrete group action, then fundamental domain for that action, fundamental domain, is the same thing with Z replaced by gamma and R replaced by X. Okay, so this is just a generic thing. I need some open set in the topology of X, or some topological space X, with this group action. A fundamental domain for the action is you can move anybody into that domain and do so uniquely. Okay, in order to say something about, so I'm building up to, I'm not going to have time to do it today, a fundamental domain. Yes, a fundamental domain for the Edels modulo the rationals, which act discretely on the Edels.
It sounds kind of wild.
It turns out it's an elementary. So it turns out I don't want to just give you the answer, but we do need one ingredient in order to arrive at the answer. So let me give you that ingredient, because that I can do in 3 minutes. We'll need to be reminded of the Chinese remainder theorem. That's all we need for this Chinese remainder theorem. It turns out. What is the Chinese remainder theorem? I don't even need the strongest form of it. So let's say given P1 through Pk distinct primes, and E1 through Ek natural numbers, and C1 through Ck with each Cj in Z mod Pj to the Ej Z. So you just give me any of these, then I can solve, there exists an integer solution to the system of equations X is congruent to C1 mod P1 to the E1, X is congruent to C2 mod P2 to the E2, and so on. X is congruent to C, this K of them, K mod Pk to the Ek. All right. I'm not assuming you've seen this before. Let's do an example, and then you'll know exactly how to do the general case, and then we'll call it quits for today. What mod? Let's say 3 squared. Mod, I don't know, 5, maybe mod 7. Give me some numbers. Give me a number mod 9. 9, 0, 2. Mod 5.
7.
2, mod 7, 5. Beautiful. Okay. So can I find a number x, which is 2 mod 9, 2 mod 5, and 5 mod 7? How do you find such a number? So let's do the algorithm, and then that you'll see why that's the proof. So let n be equal to the product of all these. So this is the 3 squared times 5 times 7. Doesn't matter what that number is. I'm not going to do the arithmetic. And let ni and j, whatever, be this number n. So of course, this is like the proof and the example at the same time. So this is a product of pi to the ei, I ranging from 1 to k. I want to take n and divide out that number. Divide out pj to the ej. So in other words, n1, so this is p1 to the e1 and c1. This is c1, this is p1, this is e1, and so on. Okay, so n1, what is n1? I take this number and I divide out by I get rid of that prime. So it's just 5 times 7. N2 is n divided by 5. Everybody following? I know I'm going very fast, but I think this is something that a lot of people know. And anyway, it's completely elementary. 3 squared times 5 times 7 divided by 7 is just 3 squared times 5. Okay, that's these numbers. Now find, so then nj and pj to the ej are co-prime. So there exists uj such that nj times uj is 1 mod pj to the ej. Okay, so u1 is a number that needs to be 1 mod 9. 35, I need to multiply by something that's 1 mod 9. 35 is almost 36, and 36 is a multiple of 9. So -1. Negative 35 is 1 mod 9. Okay, u2. I need to be mod 5. I need to be 1 mod 5. This number is 9 times 7. 9 times 7, 63 mod 5 is 3. 3 times 2 is 1. Is that right? I hope someone's checking. I'm just doing this on the fly. I need something that's 1 mod 7. 9 times 5 is 45. 9 is 2. 2 times 5 is 10. 10 mod 7 is 3. Okay, so what's the inverse of 3 mod 7? It's not 3, 4, -2. Thank you. -2 times 3 is -6, which is +1. So -2 works perfectly well. Okay, so I found these numbers u. There exist numbers u, so that n times u is 1 mod p to that power. And then it's very simple. You let x be equal to c1 times n1 times u1 plus c2 times n2 times u2 and so on, plus ck times nk times uk. And I claim that number satisfies our property. Let's see why that's the case in here. C1, we want it to be 2 mod 9. So C1, N1 is 5 times 7, and U1 is -1. Okay, C2 is 2. N2 is 3 squared times 7. U2 is 2. And 5 times 3 squared times 5 times -2. I claim this number does what we want.
Hooray!
Let's look at this number mod 3 squared. Mod 3 squared, this is 0 and this is 0. But this mod 9, this is 1 mod 9. Okay, so x mod 9, this is 1, this is 0, and that's 2. X mod 5, mod 5, this and this are 0. 3 squared times 7 times 2, that's 9 times 2, 18 times 7. I'm not going to multiply that out. That's 3 times 2, which is 6, which is 1. And then I have a 2. So indeed, I'm 2 mod 5. Everybody see what I'm doing? And x mod 7. Okay, it's clear, right? So this is 0, this is 0. This was made to be 1 mod 7, and then I have a 5. So obviously, I'm 5 mod 7. And that's the general. It's not the most general Chinese remainder theorem because I'm assuming that these are all co-prime, but this is the solution for. Here, there's always a solution. And that's-
Assuming no contradiction with-
That's right. Assuming there's no obstruction. So next time we will use this fact to try to understand a fundamental domain for the action of the discrete action of the rationals on the ring of
Like
Adeles
just this version of the Chinese remainder theorem.
is all that will be needed. All right.